Okay, welcome. How you guys doing? So you found the video and the web work, most of you. Good. So I'm Mark. You can call me Mark. That's fine. I'm comfortable with that. And I'll find out who you are here when I take attendance. Let's see. I guess we'll talk about this. We'll go through the syllabus on Friday. The main thing is that, or not the main thing, but one thing is that the final exam is known today. We know it. It's Tuesday night, April 30th. Is that a Tuesday night? April 30th, Tuesday night. It's known. So you make your travel plans accordingly. Don't make your travel plans so you miss the first day of class. Okay? Don't make your travel plans so you miss the final exam. Get it? That was a joke. But so you know that it's April 30th, that evening, Tuesday night. We know that ahead of time. Okay, so make sure you're here for that. But I'll see if we need to talk about anything more in the syllabus on Friday. But it's there available for you to read, look over. So let's just quickly with WebWorks, and most of you have figured it out. But I just want to give you a few tips about WebWork. A really important thing about WebWork is that when you put your answers in, WebWork can be your calculator for you. You don't have to have a handheld and punching out numbers and getting decimal approximations and then going to WebWork. So it can be the calculator for you. For instance, 3 plus pi squared divided by 8 minus the square root of e. So you can put in expressions like this for your answer, and it will do the work for you. And there's a lot of advantages to this. The first thing is there's a preview answer. So I give limited attempts because I want you to go slow and think about what you're doing. I don't want you to guess, okay? So I give limited attempts. The preview answer does not use an attempt, but gives you an image of what you've done. So it shows you an image here of what you've put in. And so you can make sure that you put in what you wanted to put in. I say, oh, no, that's not what I wanted. I wanted 8 minus radical e in the denominator. So I need to put, say, parentheses here, like this. Okay, and then you preview answers. And then look, I didn't waste an attempt. It told me, you're doing something wrong here. There's an error here. Because I just did 8 minus square root, and I'm not taking the square root of anything. And I said, oh, I put that parenthesis in the wrong place. I didn't mean to put it there. I meant to put it here. And then you can preview as many times as you want. And then say, okay, that's what I wanted. Now, and then answer the other ones, right? Answer the other ones. Now I got answer A the way I want it to look. That's what I think it should be, 2.0263. And now I want to use an attempt now. Okay, so take advantage of this. You can put in expressions and get a nice image of those expressions that you put in to make sure it's what you wanted using the preview answer button. Okay? On top of this, sometimes there's in the coding on these problems, there's like a tolerance to the answers. Like you have to have so many decimal places, and it gives only so much tolerance. If you do it this way, you're putting an exact result, and you never have to worry about that. You never have to worry about how many decimal places is it asking for, right? So this gives you a way to just enter an exact result, and then that if your expression is correct, you'll always get it correct. You would never be off by some decimal approximation. Does that make sense? So really, really helpful tip. You can use the email instructor button. So don't send me a separate email like with a screenshot or anything if you have a question. Go down to the bottom of the problem page and use the email instructor button. This gives me a direct link to your problem. You guys have different problems, okay? All students have different problems. So and then give me a specific message about what's going on. Don't say I just don't get this one, or I can't get it. I can't get the right answer. Tell me what your progress is, where you're getting stuck, which of A through E, which one is the one you're not understanding or whatever that is. So give me specific feedback on where you're having trouble. You can also send me a separate email with like a photo of your work. That sometimes is really helpful too. So send me a separate email and say, this is that web work problem. Here's what I've done so far on it. Okay? And that is really helpful too. But always at least use the email instructor button, which is at the bottom of every problem page. Okay? Any other questions about using web work? And then just watch those attempts, right? So sometimes I give, like if it's multiple choice or matching, you may get as few as 2 or 3 attempts. True or false, 1 attempt. Okay? And then open-ended, you'll get 5. Maybe later in the semester when the problems start getting harder, we'll maybe give you 7 or something like that. But so just keep track of your attempts. Any questions on web work? Okay, so let's jump right in. Where are we starting today? Oh, so I am, like the recording that you watched for class, on Monday's class, I will screen record all the classes. And so those will be available later in the day after class, same place that you found the first one. That's not a substitute for coming to class, absolutely not. What this is about is, so here's this may be your experience, is that when you come to the end of the class, you'll think, oh yeah, I was with them the whole way. I understand 95% of that. That was good. I was right there. But then you have all these other things in your life. 3 hours later, 6 hours later, 9 hours later, this is fading, right? This class is fading, all the connections we made, things we talked about. So that's where the video comes in. You watch it that night, you watch it the next day, you can pause it, you can take notes. So you're reinforcing, and now you're really learning it, right? You learn by repetition, right? So you can understand it perfectly the first time, but then there's a memory issue, right? So to really know it means working on it, repeating practicing your understanding of things, going over it so you can use the video to pause and take notes. But I will take attendance, and coming to class is crucial, okay? It's not a substitute for coming to class. Other questions? Okay, so I see I'm gonna have to get you guys fired up here. This is Calc 3. This is the coolest calc of them all. This is so cool. It gets really fun, but it's hard. It's hard too. Okay. Okay. So that's the videos. So I will make homework posts. So homework will consist of, you'll have web work. Pretty much every class will be a web work due. What did I make it? 11 a.m. Did I make it? No. So this one I made 5. Okay. So I may vary that. Sometimes I may want you to have it done by 11, so you've worked on it for the next class. Sometimes I'll feel like we'll need to touch on some things in the next class, and I'll make it due like at 5 or midnight that day. Like today's is due at 5. Okay, so there may be some things that we go over today that will help you with a few of those problems that we didn't maybe get all the way through in that first video. Okay, so just really, so web work will be like every class, but watch that time that is due. It may change. It may be 11 a.m., it may be 5 p.m., it may be midnight, just because of timing of things. So, but I'll try to make it as consistent as I can. And then we'll have written homework due once a week, okay? And then you'll be working on you'll first get introduced to the written homework problems in recitation, and there'll be a lot of group work in recitation, working on that, and then that you'll do a formal write-up and submit that like the next week, the written homework. Okay, so did we have recitation yesterday? Are they all tomorrow? Or are they all on Thursday? Okay, so yeah, go to recitation tomorrow. It'll be a full day with math content. Make sure you go to recitation tomorrow. Everyone has Thursday recitation, is that right? There's 2 different times on Thursday? Okay. Very good. Okay, let's jump in. So vectors, right? So this is a course in vector calculus. So we better know about vectors, right? We better know vectors inside and out. So let's just start with when you write vector in component form, huge point here. This is going to frame your understanding of vectors and be able to use them and work with them, you really have to understand, what do those components mean? When I write this vector, say vector C, and when I say the x component is 4 and the y component is -7/2, you have to know what those numbers mean. So did you pick that up from the first class? And what do the numbers 4 and -7/2 mean? Volunteer. Yeah.
4 is the change in x.
Yes.
And then -7/2 is change in y.
There are changes in those, right? Change in x, change in y. So that would be that meaning, that definition would work if C was a displacement vector, right? A displacement vector, or if we're just graphing it in the plane. And where does the vector C4 -7/2? Where does that graph in the plane? Where does that graph in the plane? What's that? He said anywhere. Agree? Yeah. So vectors are mobile. You can move a vector around without changing what the vector is, right? Vectors have magnitude and direction. They don't have a particular location or position unless you're choosing it to put it somewhere, okay? All right, so then these don't have to do with position in as much as they're just changes, right? Changes, change in x and change in y. Okay, so if you have a velocity vector, and that's 4 -7/2. So now, are they changes? What are the 4 and the -7/2 now, if you have a velocity vector? If your velocity vector is 4 -7/2, it's not really changes anymore, okay? This is a great way to think about it. But say you have a velocity vector. Now the 4 and -7/2, what do those components mean? And then, what would that mean now? Yeah. No, because it's a velocity vector. It's just that we're dissecting the velocity into x and y components, right? So basically, this is the speed in the x direction, and this is the speed in the y direction. Does that make sense? So another way to think about vectors is with the components is it's like you're dissecting whatever it is you're quantifying. You're dissecting it into an x component and a y component. Again, though, this is mobile. It doesn't have a specific location in the plane. Its location is whatever object is you're modeling, and it has that speed at that moment in time. Okay. All right. So let's do a force example here. So here we go. We got force vectors A and B are applied at the origin as shown. Find the component representation of each vector, and then find a vector that gives resultant force at the point, both in component form and polar form. So component form, let's just make sure we got those. Component form is like this. An x component, a y component, and then if it's a vector in R3, you'd have a z component. Polar form is polar form is more like the way we understand a vector. A vector has magnitude and direction, right? And so these are in polar form. The magnitude being the magnitude of the quantity that you have, or the length of the vector if you draw it, and direction being the standard trig angle, right? So that the angle. So in this case, for vector A, that's our standard trig angle, right? Swept counterclockwise from the x-axis, right? So this is also in polar form, but at 10 degrees isn't the standard trig angle. But the diagram shows you what that 10 degrees is. So component form is when you have the individual components, you use the chevrons, right? Polar form is when it's given kind of the way we understand vectors as they have a magnitude and a direction, right? It's a quantity that has magnitude and direction. Okay, so this is your task. Find the component representation of each vector, and then find a vector that gives the resultant force. So let's just talk through it, and then I'll put you to work while I take attendance, okay? So we want to find the component representation of each vector, right? So this is given in polar form. So how do I write vector A in terms of an x and y component? So if I have its magnitude and direction like that, how will I get the x and y components of A? Yes, sir?
By the magnitude by cosine or sine party.
Right, so you should recognize that this is really a trig problem, right? The x component of that vector that's the x component of A. And you should recognize that's a trig situation, right? You've got the angle and the length of this right here, and so here are your two components of A. This is the y component. So this is x, and this is y. Okay, so you want to do that for both vectors. Find A and B in their component form. And then what about the resultant? So we're pulling at the origin here with force A and with force B. So the resultant so how do we combine those to get, say, one force that would be equivalent to pulling 4 kilonewtons this way and 2 kilonewtons this way? We want the equivalent one force to applying both those forces. What's that a matter of? How do we do that? Somebody new. So if I'm applying this force, and I want, say, if I want to resolve those together, combine them to get the one equivalent force to applying those two. What's the idea there? Adding the vectors, right? We're just adding them together. We want the total sum of A and B. So is it 6 kilonewtons? No, because we got direction, right? This is the whole point of vectors. Direction matters. Direction changes everything, right? So it's not going to be 6 kilonewtons, but what will it be? It'll be the sum of A plus B. And that's the beauty of component form. So polar form, not so easy to add and get, but component form is beautiful to add, right? So you're going to find the component forms of those, and then A plus B is going to be the resultant force, or the one force that would be the same as applying those two. And then you want you to go backwards and find the component and polar form of A plus B. So I'm going to take attendance. You've got all the work to do here. So you're either making progress or you're getting help, right? So make a friend, work together, make a group of 3. So no group's bigger than 3, or if you're by yourself, you're making progress, that's fine, but you're making progress or you're getting help. Go. Okay, so you guys keep working, and I'll just ask you guys, what'd you get for the components of A?
40 cosine.
And what'd you get?
4 cosine.
B is? All right, we got to be careful here. And? Okay, good. All right, how about B? Is it 2 cosine 10, 2 sine 10? Your x, notice your x component has to be negative because we're pointing left, right? So, or you could do, how could you write them as both positive?
1 170.
Yeah, if you wrote 2 cosine 170 and 2 sine 170, then that would automatically make it negative, right? Because the cosine of 170 gives you the negative sign. Or do negative 2 cosine 10. Either way works. Get you the same thing. Okay, so then how do we get A plus B? Yeah, and how do we add vectors? So easy, right? So here's the beauty of component form. You've got vectors pointing in different directions. But by getting their components, you resolve both of them into x and y. So now you have apples to apples and oranges to oranges, right? So if I want to add these two vectors together, we can add x components because they're the same direction. We can add y components because they're in the same direction. So it's all about, getting a universal direction, right? A universal set of directions. X horizontal and y vertical. And that gives us the ability to add easily. So after you do the math, let's get an approximation then for A plus B. What's the x component approximation?
1.095.
Someone else get that? 1.095? Cool. And then what's our approximation for y?
2.918.
2.918. Are we good? All right. Now I want to get that in polar form. So let's just, if we sketch that. So let's actually sketch A plus B here. So remember how you sketch, if we do A plus B, then we're going to apply A, and then starting at the tip of A, we're going to put the tail of B. Vectors are mobile, right? So there's B. And then A plus B is going to be how the crow flies, right? Or it's starting from the very beginning, ending at the very end. So what's the one vector that does both those in succession, right? So it's this. So then we look at what we got mathematically and we say, does that make sense with this visual of A plus B? The fact that my x component is about 1 and my y component is about 3. Does that make sense with the visual red vector that I drew? Yeah, right? Looks good. The y is about 3 times as much as the x. Okay, now how do I get the polar form then? How do I get the polar form of A plus B? I've got the components. How do I get the magnitude? Right. So that was from the first class, right? So we can write that as single. So you'll see it sometimes with single bars, like absolute value, or sometimes you'll see it with double bars. It means the exact same thing. It means what's the magnitude of that vector. And by the Pythagorean theorem, if we have the x and y components, we're just using the Pythagorean theorem, right? So it's the square root of that squared plus that squared. And so we're back to, we got another approximation based on approximations here. What'd you get? Nice and loud. 3.12. Someone else get that? Approximately. So 3.12 kilonewtons. Notice it's not 6. It's anything but 6. Right? Direction is huge, right? Direction changes everything. So, yep. So 3.12. And now how am I going to get how do I get an angle out of this? Remember how to do this? Remember your trig? So if you have x and y, yeah, go ahead.
Arctangent?
Yeah, right. So if we did arctangent of what?
X over y.
X over y. Agree? Arctangent of x over y. What is tangent? Tangent is opposite or adjacent. And so which is x and which is y? Yeah, so opposite will be y and adjacent will be x. So it'll be the arctangent of y over x. Anyone got it? 69.44 degrees. Somebody else get that? All right, good. Does it look right in the picture? That it could be about 3 kilonewtons at about 70 degrees. Does that agree with our sketch of the red vector? Yeah. Questions on this example? So the beauty of having component form is if you are adding and subtracting vectors, it makes it a breeze because you can combine all the x coordinates because they're in the same direction. Add or subtract all the y coordinates because we got the same direction. Doesn't matter when you're using those universal directions of x and y. Yeah. Ada.
How do you write
Kind of.
just a column?
Yeah, I mean it's just like magnitude and direction.
Just separate by column, but
There's not like, yeah, sure, if you want. Sure, yeah. There's no like convention for that. The way there's a convention for a component form. It's just somehow you indicate what the magnitude is, and somehow you indicate direction. Yeah. Some angle. It doesn't have to be the trig angle, like they use the 10 degrees there is not the standard trig angle, but just somehow indicating magnitude and direction. But they won't ask for polar form in web work, and then you have to enter it the right way. So that's what you're thinking. That won't be an issue. Okay, other questions? Cool. So based off this example, I have a few more questions. All right, so let's just talk about scalar multiplication. What is the effect of multiplying a vector by a scalar? Did we cover scalar multiplication in the first class? Yes, good. What's the effect of that? You've got a vector, and you multiply it by a scalar. What does that do? What's the resultant vector compared to the first one? A ratio? So vectors have magnitude and direction, so let's talk about it in terms of those two aspects. How does the final vector compare to the original vector in terms of magnitude and direction? Same direction? Same direction, unless negative. If your scalar is negative, then you get the opposite, exactly the opposite direction. And then, so then how does the magnitude change? The word scalar comes from the word scale, right? What does scale mean? Magnify or shrink, right? Magnify or shrink. So that scalar that you multiply by magnifies or shrinks the magnitude of the vector by that constant. So for the previous force example, these are using find 3a. And so we'll just talk. Let's not do it. So to find 3a, you just multiply the components both by 3. And then you get a vector in the same direction to a that's 3 times the magnitude of a. And then to get negative 0.5b, what's the direction of that compared to b? Opposite direction, and the magnitude is half of the original. So it'll be in the opposite direction with half the magnitude. And to get it, you'll just take negative 0.5 of both components. All right, so this is, we've already kind of talked about this. So by multiplying by a scalar k, you get the same direction as v or opposite direction, and it scales the magnitude of v by a factor of k, right? It scales the magnitude of v by a factor of k. So did we talk about unit vectors in the first class? We might not have said what. Did I say what it was? Okay, so yeah, some of you may know what it is, but I don't think I'd mentioned it. So unit vector, real important here, is a vector with magnitude equal to so what's the magnitude of 3i minus 5j? So that's just another way of saying what? 3i minus 5j is another way of saying 3 negative 5. And those are mathematically equal, right? Because the vector I is what vector? 1, 0. And the vector j is 0, 1. So you could actually do the math there. You put 1, 0 in for I, and 0, 1 in for j, and you do the multiplication and do the subtraction, you get this exact vector. So it's not just that this is like just another way to say it. It's these are equal. These are mathematically equal. Okay. So what do we want to do? So I want the same direction as this, but with a magnitude 1, because I want a unit vector. So that means what? Scaling that vector, right? So what is the magnitude of 3 negative 5? Square root of 34. So we got to think, here's this magnitude of this vector square root of 34. How would I need to scale that so that its magnitude is 1? Yes, sir.
1 over square root of 34.
Yeah, so we're going to take 1 square root of 34th of that, right? That's how we want to scale. That's going to be that scaling factor that we're going to need to get a unit vector in the direction of 3i minus 5j. So if I take, so that should make sense. That will scale it. If that's the magnitude of this vector, that will scale it so that the resulting vector would have a magnitude of 1. Does that make sense? So then what about if we needed to find a vector with magnitude 8 in the opposite direction of 3i minus 5j? So just think about that. And the hint is unit vector. But we got to go on. But that's an important skill to be able to do, right? So now I've got this one has square root of 34. How would I have it in the opposite direction and scale it to magnitude 8? So we can think about that. All right, so I think that's good. Okay. So I want to show you this. I'm going to just a couple random thoughts here about R3. So where's our x-axis here? Coming out of the, so we render it this way, but really the x-axis is markers. Really, when you look at that picture, you should be thinking this is the x-axis, right? And the plane of the screen is what plane? The plane of y and z. Okay, y and z form the plane of the screen or your page, and x is like this. So that when you look at that picture, this is what you're imagining. Okay? So then your xy plane is when we take the x, it's the same xy plane that you've always dealt with. So let's draw it over here. So, but it's like flipped and rotated, right? So I'm going to take this, I'm going to pull it off the board like this, I'm going to turn like this, and I'm going to lay it down. It's the same xy plane you've lived in for your whole math career, but it's just flipped and laid down, right? So again, pull it off, turn it like this, and I got x here and y like this, and then I'm going to lay it down like this, and now it's the way it's oriented in R3. Okay. So then our standard trig angle is going to be important in this course. So standard trig angle is what? Rotated counterclockwise from the positive x-axis. So where's that? Can you imagine that in the horizontal plane in R3? You should be thinking it's like this. That's our standard trig angle theta in R3. Do you see it? So this causes issues because things are rotated and and transformed. But you have to see that those two angles theta they're not the same the way I've drawn them, but that's the same quantity, right? Same quantity. Rotating counterclockwise from the positive x. Okay, then there's the four quadrants, right? There's the four quadrants. 1, 2, 3, 4, and then in R3 there's 8 octants, and they're kind of the same. They're exactly how you would do it to make it coincide with the 4 octants. So let's see that. So this is the first octant, right? So let me draw if I draw the 4 quadrants here in R3, it would look like this. 1, 2 back there, right? 3 over here, and 4 back here. So those are 4 octants in the plane. Sorry, 4 quadrants in the xy plane. So the octants follow that same numbering pattern, and the first 4 octants are when z is positive. So I'm showing octant 1 right now. There's octant 2. There's octant 3. So above the xy plane, but above the 3rd quadrant. And then there's octant 4. And then the 5, 6, 7, 8 are directly below 1, 2, 3, and 4, where z is negative. Make sense? So there's 5, 6, 7, down and below. Oops. And 8 is over there. Does it make sense? So lots of times it'll say in the first octant, right? That's the nice one. Everything's positive. First octant. Okay. So it's just random thoughts here. Just language and positioning. Okay. So I've got, here's the vector 2, 3, 4, maybe. All right, so here's the vector 2, 3, 4. And so what I've done here is I've put that vector with its tail at the origin. If you take a vector and put its tail at the origin, that's called standard position. And something special happens. Standard position. So what happens when we do that? Mainly, what's the coordinates of the tip then? What are the coordinates of the tip when you put a vector in standard position? Same as the components of the vector, right? Because from the origin, if you make those 3 changes, you'll be at those coordinates, right? So what's the coordinates of this point right now at the tip? 2, 3, 4. That's the only time that happens. Make sure you distinguish between locations in space, points, and vectors, which are like changes, right, or components. Those will be the same when the vector is in standard position, when the tail's at the origin. Okay, so I have a little exercise for you here. What do we have, 7 minutes left? Why does it always take longer and longer every semester? Okay, so here's the midpoint of this box right here. I'm calling that point A. And this corner of this box, so this box is showing you, giving you some visual on what the vector, the 2, 3, 4 vector is. So A is the midpoint of that edge of the box. B is this. So can you find the distance from A to B? Or can we think of a road map to find the distance from A to B? And the hint is, use what we're learning in class, right? Use concepts that we're learning in class. So what could we do to find the distance from A to B? So normally I'd give you 5 minutes to work on this, but we don't have the time to do that. So someone, yeah, tell me. What do you mean by that, B minus A? So B and A are points. So when you say B minus A, what do you mean?
You find the distance from origin to B and origin to A, and then like you use
Okay, so maybe that would work, but I never heard kind of the key element here that's going to be involved here. So what do we want to use to help us with this? Yeah.
Or you can find the vector from either A to B or B to A, and then find the magnitude of the vector.
There we go. So we could find vector AB, and then find the magnitude of it. And that would be the distance from A to B, is that right? So how are we going to find the vector AB? We're going to get the point B. And what is point B? 204. And what's point A? You guys agree? 130?
Yeah.
And so vector AB is, so the vector starting at A, ending at B will be 1, -3, 4. Following? And then the magnitude of that will be that distance from A to B, right? The magnitude of the vector will be how far it is from A to B. So notice if B was x2, y2, z2, and point A was x1, y1, z1, then what would the distance be? If you're thinking about the magnitude of AB, then that distance equals square root of what? x2 minus x1 squared, because that would be the x component of that result, that vector from A to B, plus y2 minus y1 squared plus z2 minus z1 squared. So that then like gives you a distance formula that's kind of we use vectors to figure it out, right? We created the vector AB, got the magnitude, but then this doesn't really ever, that kind of bypasses that, right? It just takes you straight from the coordinates to the distance between those points. But we saw how creating the vector and finding its magnitude got us that. So this is the distance formula in R3. Right? This is the distance formula in R3. So if I wanted to find, say, all points from this point. Okay, so now here's point C. Here's point C right there, okay? I want to identify all points that are a distance of 2 away from C. What is the coordinates of C? 2, 3, 0. Okay, that's C. And so when I want to model all points, how do I represent that? All points. No, algebraically, mathematically, I want to represent, say, all points. What do I need? I can use variables, right? I can use variables. So all points I could call x, y, and z, right? So this is all points, and I want them to be a distance of 2 away from point C. So could you set that up? Could you set that up? All points, meaning every point x, y, and z that is a distance of 2 away from C. How would I set an equation up to do that? So here, remember, distance is, we came up with this, right? So my distance is 2 would equal what? Square root of x minus 2 squared, y minus 3 squared. You see, I'm just using the distance formula, but now my distance is known, but one of my points is not. And so then it'll give me every point that has that distance away from 2, 3, 0. So sometimes we like to get rid of square roots because they're Not fun. So if I get rid of the square root, what do I have? X minus 2 squared plus y minus 3 squared plus z squared equals 4. And what set of points is that? Right, all points equidistant from a point in space will give you a sphere. So if I come over here and if I put that in, x minus 2 squared plus y minus 3 plus z squared equals 4. I want to use transparency. I'm going to get all points that are 2 away from point C, and that's a sphere. So then that gives us the equation of a sphere, which is all points meaning x on the sphere are x, y, z. If A is B and C is the center, and what is 4 relative to this sphere?
Radius squared.
Right, the radius was 2, right? The distance from that point out to the edge was 2. So 4 was, we squared it to get rid of the square root. So this is radius squared. So A, B, and C is the center. X, Y, and Z are all points on the sphere. And R is the radius.